In this problem, we'll be using a technique, so-called the indicator random variable, to make a problem that seems very difficult actually quite easy. Now, we're given a group of n people going to a room, where upon arrival, each person will receive a random seed number, so that we call xi the seed number received by person I. For example, if we have 3 people, then x1, x2, x3, the sequence could look like 1, 3, 2. In this case, person 1 goes into C1, person 2 into C3, and person 3 into C2. Now we'll assume that such arrangement is uniformly random in the sense that any sequence of seeding arrangement is equally likely to occur. Now for each arrangement, we'll define n as the number of inversions, where inversion is defined as the following. So for every two numbers, I and j, we say there's an inversion occurring to I and j if I is less than j, but xj is less than xi. In other words, the person with a lower index actually receives a higher seeding number. If this is true, then we say there's an inversion occurring to the pair I and j. Now, the number n simply counts the total number of inverse pairs in such a seeding arrangement. For example, in the previous example, x1, x2, x3 being equal to 1, 3, 2, we see that the only inversion that occurs is between the pair 2 and 3. So in this case, n is equal to 1. Now the question we want to answer is, what is the expected value of n, given that there are little n people in the room? Now let's try a direct approach, which is by counting. We know that there are in total n factorially many permutations of the set 1, 2, 3, and n. In other words, this is the total number of ways we can arrange n people. And 1 over n factorial is simply the probability that each permutation is used. Now for each permutation, we can count the number of inversions for, let's say, permutation sigma. Now if we were to add up this number across all sigma, we will get the expected value of n. That is iterating through the space of all permutations, and for each permutation, count the number of inversions and weighted by the probability that this permutation will emerge. Now the issue, of course, is that this is a huge summation. We have to sum over n factorially many terms, and for each term, we have to count exactly how many inversions there are in this permutation. So we wonder if there's an easier way to go about without going through the counting procedure. Now let's introduce the notion of indicator random variable. Here we'll define for each ij the variable vij as the indicator variable of the event xi greater than xj. That is, the random variable is equal to 1 if xi is indeed greater than xj, and 0 if otherwise. With this definition in mind, we now see that the random variable n can be expressed as a summation of all pairs where I is less than j, variable vij. That is, we'll go over the pair of all ij where I is less than j and count 1 if there's an inversion and 0 otherwise. Now, if we were to take the expected value of n now, which is expected value of I less than j, vij, and by the linearity of expectation, this gives us the summation of all I less than j, expected value of vij. Now, what is the expected value of vij? Well, this term is equal to the probability that xi is greater than xj. We can verify this through the definition of vij. Now, what is the probability that xi is greater than xj? Well, since we're drawing a uniformly random permutation, then the chance xi is greater than xj is exactly the same as the chance that xj is greater than xi. And therefore, we know this number must be equal to 1/2. With this in mind, we put this back into summation. We know now that the summation is equal to 1/2 times the total number of ways that we can find a pair ij where I is less than j. And it remains to just evaluate the quantity right here. Now to compute a count here, we can actually do it with a simpler set first. In particular, we'll count the pair of all ij where I is not equal to j, removing the constraint that I being less than j. Well, in this case, we know the size of this set is given by n times n minus 1. Well, n is the total number of ways to pick I, and once I is chosen, there remains n minus ways to pick j. Now, in this set, we know that if number, for example, 1, 3 appears, then 1, 3, 1 also appears. In fact, for every pair ij, there's ij and ji. However, originally we only care about the case where I is less than j, and hence we know the set we care about right here is exactly half the size of set here. And therefore, we know the original expression evaluates to 1/2 times half of n minus 1. And this gives us the final answer. Expected value of n is equal to 1/4 n minus 1. So in this problem, we were able to compute the expected value of a fairly complex random variable by breaking it down into the summation of much simpler expected values using the linearity of expectation plus the technique so-called indicator random variables.